All right, this is the horizontal projectile simulation. The purpose of this activity is to explore the motion of a projectile being launched horizontally with the simulation. So this activity covers the topics of motion, the kinematic equations, and horizontal projectiles. You can see off to the right, I've got the kinematic equations we're going to use. There's 4 kinematic equations we're using in the y direction, the up and down, that vertical, and 1 kinematic equation we're going to be using for the left to right, or the horizontal motion. Now, they're the same, basically the same equations, but the reason why we only have one for the horizontal is because it's not accelerating in the horizontal direction, right? Once we add acceleration, the equations get a little more complicated. So once you pull up the simulation from physics classroom, just follow the steps. I want to show trace path, show velocity vectors, show acceleration vectors, and then I can, oh, no. The initial velocity is going to be 10 meters per second. Come down here. There you go. 10 meters per second. The angle is going to be 0, right? So this is just going to basically be like a ball rolling off a table. And the height is going to be at 80, right? That's what we're setting it. Here we go. And 80, perfect, right? So I'll check these just to show that, hey, I've done it, right? All right, so now down here, we're not doing 0 meters per second. We'll fill that in later, right? And there's a reason why. So let's just go ahead and run this simulation as is, and we can get the time to land, and we can get that x displacement. How far did it travel in the horizontal direction? So the time is 4.041 seconds, and the x displacement is going to be 40.41 meters, right? So you can see a graph is starting to form, and I'm just going to go ahead and I'm going to jump ahead to 60, right? So you can do the rest, but I'm going to jump ahead to 60 meters per second. We're launching this thing off of the table, right? So let's just go ahead and run the simulation. And now we can get the time that it took to land. Well, once again, you can see here, even at 60 meters per second, 4.041, perfect. And the x displacement is 242.44 meters. So this is about what the graph should look like, right? The points are going to follow in that. You'll notice that the time to land, even if it's dropped straight down, 0 meters per second is going to be the same whether we launched it 60 meters. It's going to be the same time. So that should save you a little bit of time on this, right? No pun intended. So this is looking at it, hey, let's look at the time to land versus horizontal velocity. Yeah, we just saw that it doesn't change, right? It takes the same amount of time whether I just dropped a projectile straight down. Now, the x displacement versus horizontal velocity, well, it's this linear line. You can see here that, I mean, it makes sense. The faster it's launched off this table or whatever it is, the farther it's going to go. And it's a linear relationship. And well, that's kind of because of the equation that calculates it, right? It's that last equation that we have on here. The delta x equals the initial velocity or the velocity multiplied by the time interval. So you can see that why that's a linear graph. That's what that's graphing. Now we need to look at horizontally launched projectiles. So we've got 2 different motions. We're breaking it up. Vertical, which is up and down, and horizontal, which is left to right. So the vertical motion is just like a drop projectile. So we've already done this, right? It starts at the origin, it falls down. The slope of this line of position versus time graph is going to be the velocity in the up and down, and it's going to be this. And the acceleration is going to be the slope of a velocity versus time graph. You can see here the velocity is not going to change, right? So that sort of gave you the answer to this one, right? What is the shape of the slope, and what's the slope representation? What does it represent? So now we've got the horizontal motion, so left to right. So this one's a little bit tricky here, right? Now the position versus time graph, it starts at 0, starts at the origin, and it's going to be moving in the positive direction to the right. It's going to be this one, right? That center one, because I know the slope of this line of a position versus time graph is the velocity. That's what this one is, because it's moving in the positive direction. So I know that the velocity is going to be positive, and it doesn't change, right? It's not accelerating. So if I take the slope of this line, I know it's going to be my acceleration in the x direction, and it's going to be 0. It is not accelerating in the left to right direction. So that sort of gave you the slope representation is going to be the same no matter what, and that just gives you what the slope. Now, this one is asking, determine whether the position, velocity, and acceleration will be positive, 0, or negative in the 3 conditions of a horizontal projectile for both vertical and horizontal directions after it's launched. So I say after it's launched because technically the initial velocity in the vertical direction is 0. But I say, hey, after it's off the table and it's accelerating downward, what is the position, velocity, and acceleration going to be for vertical and horizontal motion? And you can get that from the graphs, just looking at the graphs. Now, when an object is launched horizontally, how does the horizontal motion affect the vertical motion? Well, you can see here that just because it's being launched off the table, it did not matter whether it did not matter how fast it was going. You can see the time interval is going to be the same, right? So it doesn't really have an effect. It did not matter how fast it was moving horizontally. Now, the question here is that when a projectile is being launched horizontally, does the vertical acceleration change? You can see from the graph it doesn't. And here's why. Like, look at the hint. What force is causing the object to fall down to Earth? And does that change? Good. All right, so once again, this is the horizontal projectile simulation.